We're next going to take up the topic of what are called solids of revolution. And the idea behind a solid of revolution is that you begin with some region in a plane, and we have here the region bounded by the function f of x equals 2x minus 5, which of course is a line, x equals 5, and the x-axis in the first quadrant. And the idea behind a solid of revolution is that you take a region in a plane, such as this one, and you swing it around some line as though on a hinge, and as it swings around that line through space, it leaves in its wake a solid. So if I were to take this thing and imagine doing that, it would look something like this. And of course the solid that it leaves in its wake is a cone. And if our desire is to find the volume of this cone, then we're going to need to figure out some way to do that. And we're going to rely, in cases of solids of revolution, on the fact that this rotation process is going to leave circular disks. If we were to imagine getting out our slicer and slicing perpendicular to the x-axis from x equals 0 to x equals 5, we would get a bunch of slightly beveled, but basically a bunch of thin circular disks. And we, of course, know how to integrate areas of cross-sections in order to get volumes of solids. So that's going to be our play. We're going to be integrating circles, or as we get a little bit farther into it, we're going to be integrating circles that have other circles sort of taken out of them. So that's the idea behind these objects. Here is another quick little example, just so you can see another one of these things unfolding. This is f of x equals the square root of x. X equals 4 and the x-axis as boundaries, and we're going to again spin this thing around the x-axis. And so if I revolve it, there's the solid. And we might want to take the opportunity here also to change the number of rectangles. What this little animation actually does is it slices the region up into a bunch of tiny little rectangles. And if I then spin this around, it gives you a little bit more of a sense for how these things might be approximated and then summed up by means of an integral. And you can also get a sense a little bit of the sorts of beveled disks that you end up seeing. Maybe we can even decrease that a little bit more and redo it. Yeah, that's more like it. So the idea is that we have these disks and we're stacking them up, and their volumes, of course, are going to be pi times the radius squared times whatever their thickness is, and we're going to let the thickness go to 0 and accumulate them up, and of course that's a natural job for the integral to take care of for us.